This conference will now be recorded.
We'll start the session now, sir. I will be introducing your profile, sir. Means I'll be reading out your profile. Then we'll start the session, sir. A very good morning to one and all. This is Mubina from the Department of Computer Science and Engineering. Before start of our one-day subject-related symposium on design and analysis of algorithm, let me take this privilege to introduce today's guest speaker, Dr. SarojKumarBiswas, sir, to all of you. Dr. SarojKumarBiswas, sir, currently working as Assistant Professor at NIT Silchar. Sir having 10 plus years of teaching experience. Dr. Saroj, sir, done his BTech from Jalpaiguri Government Engineering College, MTech from National Institute of Technical Teachers Training and Research at Kolkata, and PhD from NIT Silchar. Coming to his area of interest and specialization, it includes artificial intelligence, machine learning algorithms, sentiment analysis, image processing. Moving on, Sir taught various subjects at UG program which includes Introduction to Computing, Introduction to Switching Theory, Formal Language and Automata Theory, Computer Organization, Operating System, Design and Analysis of Algorithm, Software Engineering, Artificial Intelligence, Pattern Recognition, and Machine Learning. Not only that, there are other various subjects taught by Sir to PG students. Those are Artificial Intelligence, Fundamentals of Computer Science 1 and 2, Pattern Recognition, and Data Mining. Shri sir, can you mute your microphone, sir?
Yeah, ma'am.
Okay, thank you, sir. Moving on to
Obina ma'am, you are not audible.
sorry, there was a network issue. Okay, I'll resume this session. Moving on to invited talks, Sir had shared his knowledge at 19 various colleges and university and also act as external expert and session chair. Sir also worked under various committee of administration. Coming to project, Sir has guided 9 MTech projects, 10 PhD theses and 4 R&D projects. Moving on to his publication, there are 39 accepted or published papers in international journals, 11 papers are under review at international journal, 36 accepted or published papers in international conference. Sir has set up 2 labs. Moving to his conferences and seminars, Sir has organized 6 conferences, symposium, seminars or workshops or STTP and attended 13 workshops or STTP. Thank you, sir, for accepting our invitation in a very short notice. Now, I would like to invite Dr. Saroj, sir, to address the gathering.
Yeah, thank you, madam. Just allow me to share my PPT.
Okay. Shri Hari, sir, please give the presenter rights to sir.
My PPT is visible to everybody.
No, sir. Yeah, sir, it's visible now.
Thank you. Thank you. So good morning, all the participants, and good morning to everybody those who are present here. So today our topic is a design and analysis of algorithms. And this subject is very basic in computer science and engineering and IT, information technology. Yes, we are going to present the different aspects of design and analysis and algorithm subject, design and analysis of algorithm subject. When you read, then what things we need to study, what are the issues, what are the main objectives of this subject, we need to understand. So that part I'm going to highlight here. So within short period of time, I want to cover up most of the thing in a design and analysis of algorithms. What is the objective of that? What we need to do being the student of computer science and engineering and information technology. So in my first presentation, I try to give a definitions of algorithm and what are the characteristics of the algorithms. So here the first is the definition of algorithm. What is that here? Just I have written a line for that. An algorithm is a sequence of finite number of instructions to solve a given problem. It means what it means. Algorithm is talking about a number of steps, number of instructions to solve a particular problem. So whenever we write number of steps to solve a particular problem, then those set of instructions of the step is called algorithm. Now, if you write the number of set of instructions to solve something, whether this is algorithm or not, to validate that one, we need to have certain characteristics. So if you write a set of instructions, if we claim that this is the algorithm, this is not. So whenever the set of instructions is claimed to be, let me this one right. So claimed to be the algorithm, then the algorithm should have certain characteristics, and these are number one, the input. The input, there can be any number of inputs to the set of instructions or to the algorithm actually. And there should be at least one output. And then we have a definiteness. What is that definiteness? The instructions which are written to make the algorithm should be definite. It means what? It means that if the instructions are not definite, then the finite state machine cannot calculate it. So it must be a deterministic machine cannot calculate it. So if it is not deterministic, then in practical implementation that cannot be done. That's why whenever we write certain kind of instruction, the instruction must be specific and unambiguous. The meaning should be only one. To solve something, it must have only one path. It must not have number of paths. If it has a number of paths, if it is say ambiguous, then the problem cannot be solved. That's why whenever we write instructions should have should be say definite actually. Then finiteness. What is that actually? We can write number of instructions. Fine. Now, if those instructions doesn't terminate, then the algorithm will not produce some output. And already we talked that one of the characteristics of the algorithm is the output. So we have to write the instruction in such a way so that the instructions as well as the entire program can terminate after a finite amount of time for all possible valid input. We have to do those things, right? And after that, we have effectiveness. Effectiveness means what? We can write a set of instructions. Now, if this set of instruction is not fruitful to solve certain kind of problem, then we can say it's not effective. So when it becomes effective, it means what? That set of instructions should solve certain kind of problem with valid inputs. So when we write a set of instructions, we must be careful with all those characteristics of an algorithm, right? And after that, if we talk about, then we have here, my slide is moving or not? Hello, my slide is moving or not?
It's yes, sir, it's moving.
Yeah, fine. Now, when we talk about the design and analysis of algorithm, there are certain basic factors. We need to know those factors, only then we can do certain things. What is our intention in, say, algorithm subject? And these factors are design of algorithm, right? So design of algorithm means what? So the algorithm can be designed in different ways. There are some different kind of ways and methodologies actually, right? So these methodologies, these approaches are named as greedy approach, divide and conquer approach, incremental approach, dynamic programming approach, backtracking approach, branch and bound approach. Now, what is the need to know about design of the algorithm or design techniques? If we know all the design technique properly, only then we can make one good algorithm. We're coming, what is the objective of the algorithm subject? To fulfill the objective of the algorithm subject, being a student of computer science and engineering, we need to know the different kind of design methods and their working principle. Only then we can formulate one good algorithm actually. That's why whenever you see the algorithm book, you can have a different chapters, like say greedy approach, divide and conquer kind of thing. These are the approaches by which we can design an algorithm. So we need to know elaborately all those methods and approaches to make one optimal or say good, or to formulate a good algorithm. And after that, a factors which comes that is called algorithm validations. What is that actually? Whenever we write the algorithm, then we need to validate the algorithm. What is that actually? It says that whether, as we have designed the algorithm, whether the algorithm is capable to produce the output or to produce the correct output with all the set of valid inputs. We need to check it, right? When we design the algorithm, we need to check in this space in the algorithm validations. Here we are not going to convert the algorithm into program, but from the algorithms that we need to analyze if we give the valid inputs whether it produces the expected output or not, and that phase is called algorithm validation. If it doesn't work, if it doesn't produce, then we need to rectify it, we need to modify it, right? So that is called algorithm validation. So during design of the algorithm, one of the factors that is the algorithm validations. After that, we have here that is called analysis of the algorithm. What is that actually? Analysis of the algorithm is we have to analyze the algorithms, whether the algorithm is effective or not, whether the algorithm is efficient or not. The analysis of the algorithm can be done in say two ways, or it has two parameters. One parameter is the time complexity and another parameter is the space complexity. What is space complexity? It's talking about the whole amount of memory which is required to complete or to run the program for which the algorithm is written. That is called the space complexity. But you try to understand nowadays, whenever we talk about the algorithm, we are not bothering about space complexity. Why? Because with the advent of efficient communication and technology, now we are standing in such an era or in such a position where space is not a constraint. We can have any kind of problem, and for that problem, the required memory which is required for that kind of memory nowadays is available on an average in each and every computer. That's why nowadays when you talk about analysis of the algorithm, we are not too much bothered about a space complexity, but still we are bothering about, or we bother about too much about the time complexity. And what is the time complexity? It's talking about the total time needed by an algorithm to run to complete its operations or to solve the problem is called the time complexity, right? Means total time taken by the algorithm is called the time complexity. Now, when you try to understand this time complexity is the functions of input n. So we are going to see what is time complexity is talking about. What is the growth rate of the solutions over the increase of the input size? If we increase the input size of the problem to be solved, then how the growth rate of the solution increases? That's the objective to find. That's the objective of the time complexity. By that one, we can understand whether the problem is a tractable problem or the problem is the intractable problem. We are coming to that with an example. That if we have an algorithm, for the same algorithm, we can have a different time, or different time can arise to solve the algorithm. How? Because different nature of inputs can be there. So based on the nature of the inputs, there can be the different kind of times to complete the algorithm. However, as a student of computer science and engineering, generally we focus on three kind of time complexities, and these are, see here, the best case time complexity, the average case time complexity, and worst case time complexity of an algorithm. Now we're coming here in the analysis. The minimum amount of time that an algorithm requires for an input side is called the best case time complexity, right? That can be represented by certain kind of notations. We're coming to discuss about those kind of notations. Here we're talking about analysis of the algorithm. Analysis means we are talking about how efficient the algorithm is. And the efficiency of the algorithm is defined by the time complexity, how much time is taken by the algorithm. And here, the average time complexity is talking about the amount of time the algorithm takes for the typical input. That time is called average time complexity of the algorithms. I mean, on an average, if the input is given, if these are not worst and these are not best, on an average, whenever some kind of inputs are taken randomly from some set or from some problems, then the nature is called the typical nature. So if we have a typical nature, if we have a typical input, then the time complexity or the time which is taken by the algorithm, that is called average case time complexity. And thereafter we have here the amount of time or the maximum amount of time taken by an algorithm to complete or to solve the problem of size n, that time complexity is called worst case time complexity. It means this is the highest, the upper bound of the algorithm. The algorithm cannot take more than that. That's called the worst case time complexity. So if you try to understand, whenever we bound the algorithm or whenever we find the time complexity of any algorithm, in most of the cases, the time complexity is determined by order of n. Order of O, big O is talking about upper bound. We're coming to that, right? So somehow the algorithm cannot take more than that time. So whenever we are putting time complexity for some comparison purpose, then we need to take the worst case time complexity. Means the algorithm cannot take more than that. That's why frequently, whenever you see the time complexity series are represented by order of notations. These are the asymptotic notations. We're coming to that, right? So after analyzing the algorithm, the analysis part is over, and conclude that the algorithm is efficient, but still we don't know how to do the computations. We're coming one by one, but you try to understand here, the objective is to analyze whether our algorithm is efficient or not. So once we found that algorithm is efficient, then we have to come here, the algorithm testing. It is what? Here we are testing whether the algorithm is running properly in the computer or not. So in here we have again the two phases, and these are the debugging and performance measurement. What is the debugging actually? Debugging means if there is certain kind of error or say mistake in the algorithms, so we'll find that mistake during the run or during the execution of the program, and we'll rectify it. That phase is called debugging. So when we do algorithm testing, we will have two parameters. One is called debugging, and another one is called performance measurement. Debugging is talking about to find the fault if there is something and to rectify it so that the problem can be solved. Based on how we can find the mistake? Based on the behavior of the output, whether the algorithm producing the expected output or not. If it doesn't produce, then we can understand there is certain kind of mistake or the error. Fine. After that, we have here this one, the performance measurement describes the correct program execution for all possible data set. Already we talked about it has two parameters or the two corners. Another one is a performance measurement. In performance measurement, we're looking at whether the algorithm is producing the correct output or not for all possible data set. Means for all valid possible inputs, whether the algorithm produces correct output or not. Fine. So these are basic factors in designing and analyzing algorithms. We need to know all those things, and then when we design algorithms, we need to analyze all those basic factors so that we can design one algorithm. Now here coming next topic, right? This topic comes to this is very basic question. Then what is the need of design and analysis of algorithm subject? Why do we study actually in our course in computer science or information technology? Why we do? The reason is that presently we can have a number of algorithms for a particular task. Say the task is a sorting the number or sorting a series. For sorting, we are having a number of sorting algorithms, thousands and thousands sorting algorithms. But you try to understand, if you're asked to sort some series, then you will look for the most efficient algorithm, right? Everybody, we are trying to take the most efficient algorithms. Even now you can have a questions in your mind, sir, if we don't take the efficient algorithm, then what will happen? Sir, because as a student, In academia, we deal with very small database size, right? So time complexity doesn't matter, but you try to understand whenever we will deal with very big data, if the input size is very big, then this time complexity matters. If the algorithm is not efficient, then it becomes very difficult to get the output in practice or in practical actually. That's why if we have a number of algorithms, our objective, and if we are asked to choose one of the algorithm, then our task is to choose the most efficient algorithm out of them. Fine. So now the objective being computer science and computer scientists, our objective is to make number of algorithms which would be efficient in nature. If it is efficient, then that algorithm will be used by number of people. Now question comes, how can we design efficient algorithm? That's the question, right? Yes, we can design the efficient algorithm if we know all the design approaches, because the different design approaches are having different kind of time complexity based on the working principle. So if we know all the design technique, then only we can jump to design some algorithm. Otherwise, a stairway not. We can design, but the algorithm may not be efficient because we don't know the approaches. So being computer science student, we do need to know all the approaches. And here we have the approaches. Here already I talked about greedy, divide and conquer, then incremental approach, dynamic programming, backtracking, and branch and bounce, and many others approaches are there. Now the questions come here. That's why I have written this line. I'm reading out this line. The algorithm efficiency and performance in comparisons to alternate algorithm means now we are comparing algorithm A and algorithm B, whether algorithm A should be taken or not. The algorithm one is better if, see here, if is best described by, means if we want to choose algorithm A over algorithm B, then we need to know the growth rate of time complexity of A, which should be lesser than the B. That's why the line is written here. The algorithm efficiency and performance in comparison to alternate algorithm is best described by the order of growth of the running time of an algorithm. So growth rate of which one actually? The growth rate of running time of the solution actually, right? If the growth rate of solution of one algorithm is faster, or you can say less than other, then we can say that algorithm is better than the other algorithm. Now the questions comes to how we can analyze the order of growth rate of running time and what is that actually. That's the concern of computers. That's the concern of algorithm subject. So we're coming to discuss here now. Now we're going to talk about the growth rate, right? Already you have seen that if you want to claim that the algorithm is better, then the growth rate of the running time of the algorithm should be better, means should be faster. So how we can claim, how we can establish that this growth rate is better, so that this algorithm is better. So see here an example, just very small examples. Now we have a algorithm, and the time complexity of the algorithm is C3n square, right? C3 is nothing, C3 is a constant, and this is the n square. Now can I have a mind that how we can find this n square? Yeah, we can find. Later we'll see that this is, you can say this is kind of algebraic expression. These algebraic expressions can be found from the program or from the algorithm. Later we'll see how it can be formulated. Fine. Now for the time being, just you consider that for one algorithm we have this kind of notations for the time complexity, C3 n square. And for another algorithms, we are having this kind of notation, C1 n³ plus C2 n square. Fine. Now, if we see the notation, this one and this one, this algebraic expression, you can say, then we can say this Cn square is better or faster than this one. So this n square is a faster growth rate. You try to understand this is the growth rate of the solution. So this growth rate is faster because if we make the value of n equals to 2, it becomes how much? 4. And here, if it is 2, then it becomes 8. The solution, try to understand 2 to the power 3. And here, what? 2 to the power 2. So this is 4 only if the input size is 2. And here, if the input size is 2, the total number of instructions, or you can say total amount of time complexity, that is 8. So now if we compare this and this, then we can say this is better, right? This is faster. This is faster. Now you try to understand here, this time complexity would be faster, right? But you try to understand with these, actually with these, whenever we have a time complexity n square, now we are having some constant here, C3 here, C1 is here, C2 is here, right? So now if we compare, we try to understand when you calculate the time complexity with the order, the growth rate of the solutions, at the same time we are having certain kind of, say, constant there. Now if you compare this one and this one, then no doubt we can say this one will become faster because here we have n square. But you try to understand we are having this constant, so this one will be faster only for the large values of n. If the values of n is very large, then the values of C1, C2 and C3 cannot affect on the order. But you try to understand whenever the values of n is very small, whenever the value of n is very small, then either of the algorithm could be faster depending on the values of C1, C2 and C3. So you try to understand, if you want to compare two algorithms with n and the order of n, then if the value of n is very small, then either of the algorithm can be faster. Based on which one? Based on the values of C1, C2 and C3. As C1, C2, C3, these are the part of the time complexity or part of this expression. That's why to compare between two algorithms, we have to assume that the value of n is very big. The value of n is very big. Otherwise, the assumptions may not be right. See here. Now, if we consider the value of C1 is 1, value of C2 is 2, and value of C3 is 100, right? In this case, this one becomes much more faster than this one if the values of n is less or equals to 98. So you try to understand whenever we are having a small values of n and that is below or equals to 98, then we can't say that this one is a faster, then this algorithm becomes faster. So now we need to bound, or we need to give some threshold value for this n whenever we want to claim that this algorithm is faster than this, and this is possible. See here the equation here, if we have the values of n that is greater than 98, in this case whichever can be the values of C1, C2 and C3, then each and every cases we can see this time complexity is very much smaller and this one is faster than this one, right? So if we have the values of n greater than 90 and 98, then whichever can be the values of C1, C2 and C3, it doesn't have the impact in the performance of both the algorithm. So for some threshold values of n, then for all the instances we can say this algorithm is faster than this one. So we need to have certain kind of values for n. For that we can claim that this algorithm is faster than this one. The value for which, or the threshold value of n for which our claim is valid, that value is called break-even point. That n value is called break-even point. So in this case, our break-even point is greater than 98. So we need to write 99 or greater than equals to 99 is the break-even point. Fine. So you try to understand whenever we want to find the time complexity, we have to find the values of C1, these are the constants C2, and at the same time we have to find the values of, that is called break-even point for n, and we need to find the values of n now. So here that we have this kind of time complexity, this kind of time complexity. Try to understand, if directly you have this one, then you can have may not have a proper analysis or may not have proper understanding for this one. Now the expression is this only, and the expression can have a number of terms here, 1, 2, 3, 4, 5 kind of 6, 7, 8, 9, 10, 20 kind of things can be here. If the expression is like that, then we cannot compare, then we cannot understand easily. For that one, we need to have a certain kind of notations which can best describe the efficiency and performance of an algorithms. From those expressions, actually, the notations what we're going to now establish, these notations are derived from these algebraic expressions, and these notations are referred to as asymptotic notations. So now using asymptotic notations, we can describe the algorithm efficiency and performance in a meaningful way, right? Again, you try to understand it. The asymptotic notation is ignored for the small values of n, already talked about. Now here, the asymptotic running time of an algorithm is defined in terms of the functions, right? So whenever we have the expression, that expression has to be established or has to be bound by some functions. Then that functions can be represented by asymptotic notations. We're coming how those things can be done. And the functions, what we're going to define here, all the functions, domain of all these functions are natural numbers and the real numbers. Try to understand. Now, if we categorize all these notations, asymptotic notations, then we can find that there are three kinds of asymptotic notations. Yeah, big omega representation, that this notation I have used here omega, but the notation can be different, right? And the big theta here, then big O. We have three kinds of notation to represent three kind of time complexities: words, average, and you can say best. Even if they are not equivalent, but we can say there is a kind of similarity. You cannot say these are the similar, right? But through the analysis, you can say, if you analyze, then you can understand it represents somehow very close to big O, close to worst kind of thing. So first, initially, we're talking about the big O notation. What is that actually? Big O notations, it defines the upper bound for a function f. You try to understand, already we claim that we can have this kind of expression. This is a time complexity for a particular problem. Now these expressions can be defined by a function, right? By a functions. Now if we can keep some upper bound for this function if, then this upper bound can be represented by O notation. The upper bound can be represented by O notation. So coming here with example, right? So say initially we're having two functions, fn and gn. So you possibly you are reading in say class in the say third year, so you know what is your function. It maps from one value to another value. That's function simply, right? So now we have two functions, fn and gn. Two functions are there, and then these functions are mapping from non-negative integers into positive real numbers, because already talked about in this case, in case of asymptotic notations, the domain of the functions natural numbers and real numbers. That's why, right? So we have two functions now, fn and gn, and now this fn equals to order of gn, because these are objectives. Somehow this function has to be bound by order of gn. So we can write fn equals to order of gn, or fn is order of gn if and only if there exists some real constancy greater than 0. Already, so we have seen here, we must have in the expression, we can have this kind of value, c1, c2 kind of things, right? So we can have some constant value greater than 0 and some non-negative integer constant in 0. That's the break-even point, such that this function, this fn, less or equals to cgn, and c is the real constant, right? With the help of, with the multiplication of these and this gn, somehow we are going to give an upper bound on the function fn. So once it is established, then the whole, these functions can be represented by order of gn for all n greater than equals to n0. So we have to find some values of n, that is called break-even point. So once we can establish one equations like this, then the functions can be represented by order of gn. So coming here with an example, that's the upper bound. You try to understand upper bound means what? In any case or in any circumstances, the time complexity of the algorithms or the time complexity of the functions what we found from the algorithm cannot be more than the upper bound. Fine. So whenever we have an upper bound presentation or the representation of the notation, we can ensure that the behavior, the growth rate cannot be more than that. And from there, we can understand whether the problem is tractable or intractable. So now see here, we have a function. Say this is fn equals to 16. 16 is an expression which is derived for, which is derived from an algorithm. And this is fn equals to 16 now. But how we can bound this 16? See here, with this notation, already we know this notation is to be required. These notations, you try to understand here. We have written this one. That's why again I had kept here this notation only. Now we have a 16. Now this fn means what? This is 16. This 16 can be written as less or equals to 16 to 1. Yes, this is true. And now we can consider the value of C, which one? 16 is the value of C. And what is Gn? Gn is only one, so one can be, right? Gn is one only. So now the constant is what? The value of C equals to 16 here. And you try to understand, n doesn't have any impact here. N doesn't have any impact here. That's why we have chosen the value or the break-even point which is greater than or equals to 0. From 0 onwards, this condition is valid. For which one? For a real constant, real integer constant, that is which one? C greater than C equals to 16. So now we can write the whole part, this part. You try to understand right here. Fn is this, Fn less or equals to 16 is what? C. And Gn is what? This is 1. So now already we know if this is, then how the notations can be written. If this is, then the time complexity can be written as order of Gn. So now we have an order here, and the value of Gn is which one? This one is a Gn, and this one is here Gn. So simply this Gn comes here. That's why now the you can say time complexity of Fn equals to 16 can be represented by order of 1. Similarly, come with an equation, because we have taken here only the constant function. So if we have this kind of a functions here, which one? 3n plus 5 we have, right? So 3n plus 5 is written simply 3n plus 5. I've written here, right? Notations are try to understand. I have written in some in different way here, in different way here, but I'm trying to tell you the exact thing. So I have written Fn here. So Fn, this is Fn actually. Fn equals to 3n plus 5, right? My objective is what? My objective is somehow this Fn has to be written by less or equals to Cgn. So now say the value of n is greater than equals to 5. Say we consider. So whenever we consider the value of n is greater than equals to 5, so if in place of 5, if we write here n, in place of 5, if we write here say n, then automatically the condition is changed. So here the condition is less or equals to, and the value of n is which one? Greater than equals to 5. So now we can add this one, and finally it becomes which one? 4n, right? So in 4n, what are the conditions? The conditions are the value of C is how much? 4. Already we know the value of C, this one is 4. Fine. The value of C is 4. N greater than equals to n0, that is what? That is 5. We have established here. So with these two conditions, now the whole part can be represented as 4n. So as it is 4n, so now what we can write? Simply the value of Gn is one, only n. So simply whenever we have this kind of algebraic equations or the function is represented by this expression, then for that one we can find the order of notation, and that is order of n. Simply order of n, because the value of Gn is this one. Up to here, student, did you understand any questions? You try to understand time complexity is the prime. If you cannot find the time complexity, then there is no need of the algorithm subject. That's the objective actually, algorithm subject. Now you can think that what is the role of the design method? Based on the design method, you can get a different kind of algebraic expression for a function to solve a particular problem, because different approaches are having different kind of working principle. So that whenever, if you solve some problem using some approach, if you calculate the whole time complexity, it can be represented like that. As again, if the same problem is calculated or computed using a different approach, then whole time complexity can be different. Right? So up to here, any questions? Up to here only, right? Later on, we can have a question that is different, but up to here, any questions?
Sir, I have one question, sir.
Yeah.
Sir, I have O of n means it stands for order of n, sir. O stands for order.
Yeah.
Okay, sir. That only.
Order of n. That is called order of n actually. Order of n.
Yes.
This is big O of n actually, right? So it's a asymptotic notations. It's an upper bound. The order of the growth rate. I'll show you how it differs actually. You can see the number of problems are there. How many can I do looking on that? Because I have a problem. Initially, I have to create the background. Otherwise, if I jump to the problem, then you cannot understand. So now in the next slide, we have here It's a quadratic, it is a quadratic function, right? It is this function is written like that. Fine. So again, our objective is represent this one by order of notation, big order of notation. So we have to do this kind of thing, right? We know, you try to understand always. Our objective is to produce this kind of, somehow we have to show this condition. Once it is established, then simply we can write here. Okay. So here just we have chosen the values of which one? The values of 6n square greater than equals to 16n. So in place of 16n, just we have kept here n square. So whenever n square is given, already we established these conditions. So it becomes less or equals to 27n square. So finally, if we simplify this expression, that it becomes 28n square. 28n square, right? So we got now 28n square. This is less or equals to, not equals to, sorry, this less or equals to now 28 square. So we have a fn. This fn now less or equals to 28 square. So here clearly we're looking that the value of c is how much? This is 28. And for which value of n? Here, from here you try to understand, we have taken n square greater than equals to 16n. So if we simplify, finally we'll get the values of n greater than equals to 16. That's why the n naught or the break-even point is now 16. So for these conditions, now we can write this expression. Now once we can write this expression, now this part can be represented by order of n square, because here the value of gn is equal to 1, n square. So now if we have this kind of expression, now this expression can be represented by order of n square, right? So here we have a cubic functions. In the cubic functions, what we have done, simply just I'm showing you quick. In cubic functions, what we have these equations. Again, you try to understand, our objective is to show this kind of thing. So what we can write, this is okay, fine. We have written the whole equations now here. Now less or equals to 3n cube plus n square and n square. How? Because we have assumed that value of n square greater than equals to 2n, right? So whenever in place of 2n, if we keep here n square, then automatically this condition holds true. Now we are simplifying this one. So finally we got this one, 2n cube plus 2n square. Now again we are considering this n cube greater than equals to 2n square. So after solving this one, we have which one now? 3n square or 3n cube. The n cube, I did not say parse level by level. So simply you consider this is n cube, right? So 2n cube plus n cube here, that's where it becomes less or equals to 3n cube now. So now if you summarize all those values, the condition comes here. The value of c equals to 3. The value of c is how much? That is 3. And n naught is how much? N naught can be calculated from here, can be calculated here. And finally, the conclusion is value of n naught is 2. So with this condition, now this condition holds true. So from here, simply we can write this is order of n cube such that the value of c is 3 and n naught equals to 2. So if we have this kind of cubic functions, then the time complexity can be represented by order of n cube. And then again, we have here exponential. Then an simply just we need to do an exponential kind of thing here. This is the function we have. Fine. So our objective is to prove this one. So what do we need to know now? We have 2 to the power n plus 6n squared plus 3n. So somehow now we are claiming that n squared greater than equals to 3n. So in place of 3n, we kept here n squared. So condition becomes like this. So now the equation becomes 2 to the power n plus 7n squared. Now again, we have to assume something, otherwise it's not possible. What do we assume? We assume that 2 to the power n greater than equals to n squared. And this holds true only when the values of n becomes greater than equals to 4. That's why we got here the value of n naught. N naught becomes 4 here. So now we have 2 to the power 7 into 2 to the power n. So if we simplify this expression, finally it becomes 8 into 2 to the power n. So here, try to just match with this one. Here the value of c becomes how much? That is 8. And the value of gn how much? That is 2 to the power n. Fine. So now if we want to represent it by order of notation, then simply we can write order of 2 to the power n with the constraint c equals to 8 and n not equals to 4. In that way, actually, whenever we have some expressions and this expression is derived from the algorithm, when we analyze how to derive, we're going to see, right? All the control structures of an algorithms, we're going to see how this expression can be derived. Once this expression is derived, then it becomes a function of fn. Now this one can be represented simply by some notations. So simply asymptotic notations can be found very easily. Fine. So we already talked about the big O notations. Now we are having big omega notations, right? And big omega notation is talking about the lower bound of function f. It means that the functions can take at least this time, this lower bound. The problem can take more than that, but at least this time, right? You can say this is a kind of best case. At least this time will be taken by the function to be solved, and that part is represented by big omega notation. But you try to understand this best case is rare. Best case doesn't happen, and best case doesn't have any meaning in algorithm. That's why you cannot see that the time complexity is represented by omega notations. Never it is represented by omega notations. It doesn't generally, right? And now same thing, that how we can establish, right? Here, same thing, we have two functions. This is fn, and here we have a gn. So we have two functions, and they are ranging from non-negative integers into the positive real numbers. If it is, then this fn is omega of gn, means this fn can be bound by the lower bound, this omega of gn, that's the lower bound, if and only if there exists some real constant c greater than 0 and some non-negative integer constant n naught, such that now this fn is always greater than equals to gcn, right? So this value would be always greater than these values, right? So this is what, this is now the lower bound. So once this is proved, or this is proved, then what? Then we can represent the total function fn as omega of gn, right? So now looking one of the problem here simply. So see here, simply here we have a fn, the value of fn is how much? 16. Now this 16 can be written as greater than or equals to 15 into 1. Yeah, this is true. If this is true, then this is fn. My fn is now always greater than or equals to cgn, where the value of c is how much? 15. And the value of gn is how much? There is only 1, right? And so therefore the value of c equals to 15 here, and n not equals to 0. Why? Because n doesn't have any impact here, because it's a constant function. That's why the time complexity of this constant function is represented as omega of 1, with condition is what? C equals to 15 and not equals to n not equals to 0. Now take another example. This is the algebraic equation. Same thing, right? The same thing. 3n plus 5. What's our objective right now? Our objective is to show that this fn greater than equals to cgn. That's the objective hour. If it is, then we can write the whole expression as order of gn. So see here simply that we have a function fn, and f equals to what? 3n plus 5. Now I can write this one greater than or equals to 3n, because 5 is removed from here. So 5 is more here. This one on the left hand side, I have 5 more. So and I have 5 more here. That's why always the condition holds true, greater than or equals to 3n. For which value? For when c equals to 3 and not c equals to 3. When we represent then c equals to 3. This condition is true for which condition? And not means the value of n greater than or equals to 0. The value of n is greater than or equals to 0. For this value, this condition is true, and now it is represented by 3n. So now if you compare here the cgn, then we can say 3 is what? 3 is the value of c, and gn is the value of n actual, right? So now the time complexity is represented by omega notations, by how omega of n here, and where the values of c and n naught are changed. But you try to understand, if you see for all the functions on an average in all cases of the functions, order of notations, omega of notations, both are same. But you try to understand, whenever we make it order of O and order of omega, then the values of the constant c and the break-even point, they are changed actually. They are changed. Fine, they are changed. So you see that we had some values here, right? N naught was equals to 5, I think, in case of order of O notations. But you try to understand in case of order of omega notations, it becomes n naught greater than equals to 0. Fine. So in case of quadratic equations, we have to do the same thing. I'm not going to talk about more here because otherwise we'll kill all the effort and all the time here. But similarly, the things can be done here. So finally, as the equation is like that, that's why it can be written as order of n square. But the value of c and n naught, they are changed. Similarly here, in this case, it is written as 2n cube. That's why it is order of n cube with the condition c equals to 2 and n naught equals to 0. In case of exponential, the whole part can be written as 2 to the power n, where we have a conditions n naught greater than equals to 0 and the value of c equals to 1. And now finally the time complexity can be represented as omega of 2 to the power n. Now we are coming to the next one, that is called, say, this is theta notation. What is that equal to? It is a Titan notation. It is in between lower bound and the upper bound. So now we can say it corresponds, it is closely related to the average case time complexity. It is in between lower bound and the upper bound, means this time complexity is always greater than the minimum time and always lesser than the maximum time. So it is in between, and that time complexity at that bound is called the tighter bound. So that bound is represented by theta notation. So again, so frequently the notations are represented by theta notation also, right? And here now, so how we can establish that actually. So similarly, we have a two functions, fn and gn. No need to describe. Now this fn is theta of gn if and only if there exists some real positive constant c1 and c2 and n naught, such that this kind of condition is now holds true. Which conditions? We have a function, and that function would be greater than equals to, means greater than equals to means what? This c1 gn less or equals to fn, means now this fn is greater than this value, this lower bound, right? c1 gn, and this one is lower than this upper bound, right? c2 gn. So now try to understand, whenever we want to have a mini upper bound and the lower bound, the growth rate would be same, but you try to understand we'll have a different values of c1 and c2 for some break-even point. So whenever this is established, then we can say, then we can represent these functions by order of gn with the constant value c1, c2, and break-even point in 0. So see here one example, we have fn equals to 16, right? Now this 16 simply can be written as 15 into 1 less or equals to fn, because the value of fn is how much? That is 16. This 16 less or equals to 16 into 16. Fine. So now we got it two bounds. This is the lower bound and this is the upper bound. For which one? For 16. So from here we can find that the value of c1 equals to how much? That is 15. And from here we can find the value of c2 is how much? That is 6. No, here from here this is 15. And from here the value of c2 is 16. And n naught is 0. Clear? So as it is bound, and now it is in between lower and upper. That's why the whole expression can be represented as order of gn. Gn is this one. This one is gn, right? So order theta of 1. So just I'm showing one more here so that it becomes more easier. So simply here we have a linear function here, this algebraic equations, right? So our objective is to represent this one by the theta notations. So again, for the theta notation, what is our objective? Our objective is to establish this one. C1 gn less or equals to fn less or equals to c2 gn. That's our objective. Clear? Our target is this. Now we have this one. Simply we can write from here simply 3n less or equals to 3n less or equals to 3n plus 5. For which condition we can write? When the value of c1 becomes 3, and for all values of n. And also this one can be represented how? This one can be represented as less or equals to 4n when the values of n greater than equals to 5. Because whenever we consider, already we talked about this one, whenever the value of 5 becomes less or equals to n, or value of n becomes greater than equals to 5, if 5 is represented by n, then automatically this condition holds true. That's why now it becomes 4n. Okay, so for which values? For n greater than equals to 5 and c2 equals to how much? 4. And n naught is how much now? 5. Here the n naught was 0, but here the n naught is 5. So if we have two kinds of n naught values, then we have to take the maximum, the maximum one, the greater one, to establish that the equation always true. So that's now we can represent the whole this function, this 3n plus 5. How these 3n plus 5 can be represented as now less or equals to 3n less or equals to 3n plus 5 less or equals to 4n, with which conditions? The conditions are the value of n naught equals to 5, means it is for all values of n where the values of n is greater than equals to 5. And here we have two values, Cn is which one? C1. The value of C1 is 3 and the value of C2 is how much? That is 4. Clear? So now as we have this is the middle, we have a lower bound, we have an upper bound with these conditions. So simply now these equations can be represented by asymptotic theta notation, that is theta of n. Why n? This is a gn, this is a gn. Try to understand, because now the whole part, this part is corresponding to this part. So here we have a C1, this is 3, and gn is 1, n. And you have this equations, fn, the value of fn is what? 3n plus 5. And here we have C2 gn, C2 is which one? 4. And the value of gn is which one? N. So now the time complexity of this one can be represented in terms of theta, big theta, that is theta of n. So in that way actually it can be represented. Similarly in the quadratic functions we can do, and so in this case similarly we can have a theta of n square, and similarly here we can have a cubic functions, and here we can have a theta of n cube, and then finally we can have here theta up to just exponential part I did not include here. Same thing, that's why I did not include, because it will take unnecessary time. Now the many questions are coming, and many questions will come to the student's mind. So how we can represent, because we are talking about that this is the time complexity. Now the time complexity is represented by a function fn, where this function is defined by these algebraic equations, right? Now we have a question that, sir, how these algebraic expressions come in the function, how can we calculate? These are nothing. These are what? These are the representation or algebraic representations of number of instructions in an algorithm. So now the questions are how these number of instructions can be represented like that. Yes, sir, those things can be represented like that. So these are what we are calculating. We are calculating the number of instructions of an algorithm, right? So the calculation is like now in this way. So now coming how we can calculate, looking on that, we try to understand when we write an algorithm, right, or any one program. The program is written by which one? By the control structure, different kind of control structure. All the instructions follow certain kind of control structure, right? So now if we talk about all available control structure of an algorithm or in a program, then we can give the name like that. We can have a sequence that is called sequencing. Means sequencing means what? The number of instructions we have: instruction 1, instruction 2, instruction 3, instruction 4. Whenever we write one program or algorithm, we write like that. Already we talked that what is an algorithm? Algorithm is a collection or is a sequence of instructions. So there can be number of instructions. Now those instructions can be written in different ways using the control structure of the algorithm, and these are the control structures: sequencing, if then, for loop, while loop, and then recursion. Fine. So we'll have those things. Now from those things somehow we have to find the algebraic expression, and then this algebraic expression can be represented by functions, and that function has to be bound by some asymptotic notation. Then only we can find the time complexity of the algorithm in terms of asymptotic notation. So it can be order of n, order of omega, or order of theta notation. So coming here, whenever we have a sequence. So now here you say this is a program. I have a two sequence in the program. Say I have a two part. One is a P1, another one is a P2. Clear? Now the time complexity for P1 is T1, and the time complexity for P2 is T2. Say, right? Then I have to find the whole time complexity of this sequence. The whole time complexity is what? That is T1 plus T2. T1 plus T2. But again, you try to understand whenever we find the time complexity, right? Time complexity from the perspective of asymptotic notation, then we use a maximization rule. So we will find max T1 comma T2. It means what? If we have two modules, if one time of complexity is greater than another, then the greater one will be taken. Less one wouldn't be considered in the consideration in case of asymptotic notations. And if you want to include all the parts together, then you have to find the time complexity that is called amortized time complexity, amortized, where all parts are taken care. Generally, we don't focus on that. And in most of the cases, we find asymptotic notations where generally maximization rule is applied. So see here, an example you can understand better here. So we have a two part, the P1, and here the time complexity T1. P2, here the time complexity is T2. Now T1 say order of n. Say still I don't know how to find order of n. I'll show, and we'll show. We'll see how things is done. Now say we have a Tn, and the time complexity of Tn is order of n. And here I have a time complexity that is T2, and it is represented by order of n square. Say now to find the time complexity of this sequence. So time complexity, already we know that this is what T1 plus T2, and already I told you that we have to apply maximization rule, right? Max T1 comma T2. So max order of n comma order of n square. So out of order of n and order of n square, which one is greater? Order of n square is greater. Clear? So that's why the time complexity becomes order of n square here. Done? So in that way, if we have a sequence, then we can do simply here. If we have this sequence, and for this sequence, if the time complexity T1 is order of n square, and here T2 is order of n square, then again see here T1 plus T2 max T1 comma T2 max order of n square comma order of n square. So any one of them. That's why here this is order of n square. So now coming to a if else statement. What is that actually? Already you know if else. So if it is true, then this part is executed. If this is false or this is not true, then this part will be executed. So now if you want to find the time complexity of this if then else part, then the total computational time becomes this equals to max T1 comma T2. So again maximization rule, right? So simply here if we have a T1, this is n square, and here T2, that is again n square. The total time complexity can be written as equals to max T1 comma T2. So max order of n square comma order of n square. So it becomes order of n square simply, right? Using maximization rule. So now coming here now, right? If we have a loop, and if it's a nested loop, it's still here we have done all those things, right? So again, I'm telling one thing. If we have one instruction, single instruction, for the single instruction, the time complexity that is a constant. Only one or some kind C kind of thing you can represent, and C is a constant. In that way, actually, it is considered when we calculate time complexity. So now we are standing here. How to calculate the time complexity of this one? By counting the number of instructions. Clear? See carefully this instruction. See, this is a nested loop, nothing else, right? So now say that in the nested loop, what we are doing, which instructions we are computed? We are computing this instruction. Sum equals to sum plus A, I, J. We are computing only this one, right? Again and again, again and again. So now say T, I, J is the computations for sum. Now say for this sum, we have a computational time, and this computational time is represented by Tij. Initially, you try to understand Tij. Again, I told you if we have one instruction, generally it is represented by some constant. And finally, we have taken this Tij equals to as 1 actually, right? So say this is the constant time. It is assumed whenever we find a time complexity, we have to assume that the instructions are one instruction is executed by a constant time. So that is the Tij, is the computational time for sum here, which is a constant value already written here. So now whole part can be represented. How? So here we have a summation of 1 to, if we talk about the outer loop, so outer loop which was summation of I equals to 1 to n, because the values of I ranges from which one? From 1 to n. That's why we've written the values I equals to 1 to n simply. And then which one? We have an inner loop. Then which one? Summation of j equals to 1 to I. And this many times, this number of times execution would be done, whether the time complexity of this execution is Tij already we have considered here. Clear? So When it is I equals to 1, this is 1 time. When I equals to 2, again 1 time. When I equals to 3, again 1 time. Means if we calculate all the summation here, then it becomes what? 1 plus 1 plus 1 plus 1 plus 1, like that. Fine. Now for each one, the time complexity can be represented by order of 1. Already we know. So if you have a 1 as a constant function, so you can calculate very easily, because already we have seen all the asymptotic notation and the big O notation. If I have a 1, then the 1 can be represented by order of 1. So now this constant is represented by order of 1. So it can be any number. It can be represented by order of 1 with some values of C and N naught. N naught is always 0. So now this time complexity, how many times? I number of times. That's why this whole part is represented by order of I. The whole part is represented by order of I. How many times? I number of times. That's why it is order of I. Clear? Now this I comes here, the order of notations comes out, and here we have summation of I equals to 1 to n. So the first iteration, the value of I becomes 1 in the outer loop. You try to understand, right? In the second iteration, the value of I becomes 2. In the third iteration, the value of I becomes 3. So now if you simplify this one, it becomes what? 1 plus 2 plus 3 plus 4, like that, natural summation of the natural numbers. And that is represented by n into n plus 1 by 2. And now if we calculate, if you make the algebraic expression, and if you want to find a bound, then it can be bound by order of n squared notation. That's why whenever we have this kind of expressions or the nested loop, for the nested loop, the time complexity is always order of n squared. If we have only one loop, the time complexity becomes order of n only, because it will run in number of times. Similarly, see here, I have here, so simply I have one loop here. This is a while n greater than 0, and I'm doing one operation, that is n equals to n minus 1. So Tn is the computation time for n, and it's a constant. Now if you want to calculate the time complexity of this control structure, then it becomes what? Time complexity equals to summation of j equals to 1 to n, this Ti. This is 1 and this is 1, already we talked about. The whole part becomes order of n. In that way, actually, the time complexities are calculated up to here. So any questions till now? We have a number of things. At least I can discuss one of the methods. At least one of the things I can discuss, I think, possibly. Tell me any questions? Guys, any questions?
Questions, sir.
Yeah, sir.
Sir, actually, when I am listening this topic about this topic, I got. So, what are the boundaries of this DAA subject, sir? Design and analysis of algorithm subject. What are the boundaries?
Boundary, actually, you try to understand boundary is simply we need to understand the different kind of design technique, and we need to analyze the time analysis. Hello. Time,
yes, sir,
time
yes,
complexity analysis, right? We need to understand, we need to have a complete understanding of time complexity analysis, because each and every time in case of DAA, we are trying to find the efficient algorithm in terms of time complexity. So you must have clear understanding about the time complexity. Clear, number one. Number two, now this time complexity is totally based or depends on the design of an algorithm. Now, one algorithm can be designed using different kind of design approaches, like say greedy, like say branch and bound, divide and conquer, then dynamic programming, then you can say backtracking. Clear? So we need to have clear understanding about all those topics. Then only we can design, try to understand, fine. And then in most of the cases, you can see in design and analysis, I don't know, did you get in some book or not? In most of the books, you can see whenever we have a DAA, we have a sorting and searching as a separate topic or the chapter. You will get. The reason is that because our objective is what? Our objective is to design the algorithm, right? So which kind of algorithm we'll design? Especially we'll design the search algorithm. Why? Because whenever we have whenever we don't have any conventional method means what? If our objective is to add 2 plus 2 addition, so we can do in the conventional method. Any conventional problem can be solved using conventional method. That's okay. but you try to understand whenever we have some kind of problem which cannot be solved directly using some conventional method, then all kinds of problem in computer science is solved using search algorithm, right? And in many search algorithms, doing the search, sorting is a part of that. So especially whenever we are going to design any algorithm, we are going to design the algorithm. This is either sorting, searching, or sorting and searching algorithm. That's why we need to know sorting and searching. That's why this chapter is added there. Because one thing is then artificial intelligence. Whenever we have a direct method to solve certain kind of problem, then there is one way that is called search technique, right? In search technique, there are number of problems I'm going to talk about, because there is a problem that with increased time complexity, the behavior of the problems can be NP-hard. So if it is an NP-hard problem, then in real time you cannot get the solution. Those become intractable problem. Now to solve this intractable problem, the researcher actually proposed a number of heuristic algorithm. One of the heuristic algorithm is the greedy, this nearest neighbor. That's a heuristic. It's a kind of heuristic approach. We're going to discuss those things. So see here, up to here. So we talked about possibly, yeah. Let me when up to actually try to understand. I wanted to have questions up to here to the students actually, because they are the listener.
Yes, sir.
We can have a number of outside of this topic some questions. So those questions would be at last. But up to here, I want to make the student understand. It doesn't mean that I'm just telling and I'm finishing the topic only.
Yes, sir. You told the time complexity analysis is a very, very
fine. Agreed, sir. Agreed.
So,
okay, sir.
Yes, sir. Students generally, I think they for BTech students, they can do like this, no, sir. They can start with understanding the concept, then with the help, they can solve an example, they can solve a problem.
Right.
Then they clearly go for a time complexity analysis.
Yeah,
So,
absolutely.
Concept, example, and time complexity analysis. So
right.
This way yes, sir.
This way I'm going.
Sir? Yes,
sir. So here already see that we have seen the different kind of control structure. We have seen the last control structure. What we had the recursive algorithm or the recursion. So when we want to find the time complexity of recursive algorithm, then we need to know about the recurrence relation, because using the recurrence relations, we can find the time complexity of recursive algorithm. Now, what's a recurrence? A recurrence is an equation or an inequality that describes a function in terms of itself. That is the recurrence. So whenever we have a recurrence problem, so how we can solve those kind of problems? Now to solve those kind of problems, we have a number of techniques here. That is substitution method, number one, then iteration method, then changing variables, Recursion tree, characteristics, equations, n to the power alpha, master theorem. Using those things, we can solve the recurrence problem. And the recurrence relation is built whenever we have a recursive algorithm. Fine. So now I'm coming with an example. So if we have a recurrence relation, then how using say substitution method we can solve it. Coming to that one, right? So now say we have this one, say we have this problem that is Tn equals to 2 Tn minus 1 plus 1. This is the problem. This is the recurrence relation now. And we have a constant this, and also one initial condition is given, that is T0 equals to 0. Now we have to find a solution for this relation. How we can do? So here for the substitution method, initially we have to make a table for that. The conditions which are given here. The condition that is given T0 equals to 0. Very good. Now I want to make the value of T1 as 1. T1 as 1. So I'm looking how much value can I get. So already we have this equation Tn equals to 2 into Tn minus 1 plus 1, right? So just keeping the value of n equals to 1 here. N. So whenever the value of t becomes 1, then it becomes what? T into the value of n is how much? 1. So 1 minus 1 plus 1. So it becomes how much? T2 into T0 plus 1. The value of T0 is how much? It is already given, that is 0. So we can keep here 0. So if you keep here 0, then finally the value of T1 becomes how much? The value of T1 becomes 1. So that's why when the value of T this one n equals to 1. T1 means what? The value of n equals to 1. Then the value of Tn is 1. Similarly, when it is T2, then we can find which one? 2 into T2 minus 1, because the value of n is how much now? 2. We have considered. So that's why 2 into T2 minus 1 plus 1. So it becomes 2 into T1 plus 1, and already we have the value of T1. The value of T1 is how much? That is 1. So now we can keep the value T1 here. This is 1. 1 into 2 plus 1. So finally the value becomes 3. So that's why when the value of n is 2, then the value of Tn is 3. Similarly, we can calculate the whole table here. Clear? So whenever the whole table is created, from this table we can guess a function or guess a solution, because we are looking that if we make these equations, right, or this expression particularly finds all the values. That's why the solution which is guessed, that is 2 to the power n minus 1. So it is guess only for all n greater than equals to 0. This is the guess only, right? Now this guess has to be proved by mathematical induction. That is our objective. Means we guess it. Now somehow we have to prove this guess, and that one can be done using say mathematical induction. So now the question, what is the principle of mathematical induction? The principle of mathematical induction is that if you want to say that pk is true for all values of k belongs to n, then we need to prove 3 things or 3 steps, and these are: pk is true, this is our objective, pk is true. Then our objective would be, we have to show that p0 is true, and also pk is true, then pk plus 1 is also true. So if we show the 3 steps, then by mathematical induction we can say the guess whichever we have taken that pk is true, that is really true. So in this case, what we have guessed? We have guessed this solution. How we can guess this solution? From here, see now, simply, if it becomes 2 to the power 1, then the value becomes 1 actually. 2 to the power 1 minus 1, the value is 1. If it is 2 to the power 2, the value of n is 2. 2 to the power 2 minus 1, the value is what? 3. 2 to the power 3 minus 1. 2 to the power 3 is how much? 8. 8 minus 1, 7. So we are looking that these are the values of n, and these are the solutions. So we are looking that if we have this kind of expression, then this expression can find these values simply. So that's why we guess this one, right? So what's our objective? Our objective is to prove this guess by mathematical induction, and already we talked about the principle of mathematical induction. So now initially we try to prove this one as when the value of n equals to 0. So we kept here because we have chosen this guess solution now. So we made it t to the power t0, because now we're taking for n equals to 0. 0 equals to which one? 2 to the power, in place of n we are keeping now 0. So 2 to the power 0 minus 1. So finding the values 1 minus 1, that is 0. So t0 equals to 0 if we guess this solution, and this is absolutely right, because in the initial condition we have given this one, t0 equals to 0. So this part is over. Fine. Now we are finding the values for when n equals to 1. When n equals to 1, we're keeping the values and looking that, yeah, it is true. We are giving the values of n equals to 2 and looking here, yeah, this is also true. We're giving the values 3 here. I did not do all those computation, right? So whenever the value of n is given 3 here, looking that, yes, it's okay. So like that, if we give the values 4, 5, 6, 7 like that, when the values are greater than equals to 0, then the variable, or up to it can be the value k also. We can consider also one value, that is k. When the value of k is greater than equals to 0, then this equation holds true also, because already we have seen that this equation is true for 1, 2, 3, 4, 5 kind of thing. So now we can assume, now we can say this is also true for k when the value of k greater than equals to 0. That's why whenever we assume the value of n equals to k, then it becomes t k equals to 2 to the power k minus 1. That's true. So already we have proved this one, and we have proved this one. Now finally we're coming to this one. How to prove this one? Coming here now, see here, already we have this equation, right? So we have taken these equations, and already what we have proved that tk equals to 2 to the power k minus 1. So now what we have done, in place of k, we have given k plus 1. So similarly we have 2, and here we have tk minus 1. So in place of k, that we have kept how much? We have kept k plus 1. So that's why in t we have kept here in place of k. Now we have kept here k plus 1. So this is k plus 1 minus 1 plus 1. So if we solve this one, then it becomes how much? 2 tk is 1 1 out. So it becomes 2 into tk plus 1. So we have a tk now, and already we know tk is how much? Tk is this, we know. So in place of tk, we kept now this one, 2 to the power k minus 1. So we kept here 2 to the power k minus 1 and then plus 1. So now we simplify, simply it becomes what? 2 into 2 to the power k minus 2 plus 1. So now if we solve this one, then it becomes what? Because this is a multiplication of 2 to the power 1 and 2 to the power k. So now we can write this one as 2 to the power k plus 1 and then minus 2 plus 1. Simply now we can solve this one as 2 to the power k plus 1 and from here minus 1. So looking that whenever we take k plus 1, again we are getting the same gauge solution. So already it is proved for when n equals to 0, when n equals to k, and when n equals to n plus 1. In all cases, our assumption is true. That's why finally we can say the case whichever we have chosen, Tn equals to 2 to the power n minus 1, that is true for all n greater than equals to 0. So the solution of this recurrence, this is the recurrence relation. The solution of this recurrence relation is this, using which equation? Using substitution method. In that way, the problem is solved actually. Now we are coming one of the design method, and that is called divide and conquer method. So already talked about divide and conquer, means it is a design method only, but now these are the characteristics of divide and conquer method. Recursive algorithms are solved using divide and conquer method. So try to understand, if you have a recursive algorithm, then those kind of algorithms are solved using divide and conquer. Whole problem is divided into sub-problems. The problems are divided into sub-problems. These sub-problems are similar to the original problem, but smaller in size. And try to understand the sub-problem should be similar to the original one, because we're going to solve the problem when there is a recursive algorithm. That's why the sub-problems are similar to the original problem, but smaller in size, right? And these sub-problems are solved now recursively. Fine. Finally, solution of these sub-problems are combined to create a solution to the original problem. Now the solution of these sub-problems are created and they are finally combined to find the final solution of the problem using divide and conquer method. Now if you find the steps which are followed generally in case of divide and conquer method, then these are the problems. The problem is divided, then we have to conquer, means we have to solve the problem recursively, and finally those sub-problems has to be combined together. So these three steps are required in divide and conquer method. So now coming one of the problem of the divide and conquer method, that is a merge sort here. How to solve this problem using say divide and conquer method. So initially we have to divide. So we're dividing. I have shown here the top-down approach. Last, how to merge. Finally in the figure we have how to merge actually, right? So don't think about that this is the first step. In the first step we have to divide. This kind of sub list are created, or sub problems are created, and again this sub problem is divided. This kind of sub problems are created. This type of sub problems are created, again divided. This kind of sub problems are created. This type of sub problems are created. Clear? So it is recursively done. It is recursively done, and finally again recursively it is merged. So recursively it is merged, and I try to understand during merge only the decreasing order is maintained. During the merge only, so ascending order, not decrease. Ascending order is if our objective is to find the ascending order list, then during the merge only ascending order is found from the two lists. Therefore, when all those things are subdivided, when you got small pieces, now okay, these are the solutions. When we merge recursively, we are solving and merging. When we merge, actually the sorting is means decreasing, or the elements are arranged in ascending order only, right? That's why merging complexity is Cn actually, right? Because you may have a questions later, we'll see. So we are merging here. We are merging, so 20, 50, and we are merging here in ascending order 40, 70, and similarly we have done here. And then we are merging this and this, right? When we merge, we maintain the ascending order, right? From this one and this one. So that's why the values now becomes 20, 40, 50, 70. Similarly here, 10, 20, 30, 60. Similarly here, we kept it 10, 20, 20, 30, 40, 50, 60, 70 like that, right? In that way, actually, it is solved. Now we are coming how the analysis can be done or how the recurrence can be formed in say divide and conquer method, especially if it is a merge sort, how to do all those things coming now here. So already it is proved that it's a recursive algorithm. So whenever there is a recursive algorithm, then the time complexity is represented by recurrence relation. Now say this recurrence relation is defined as Tn. Clear? Now this is Tn, say assume. Now how we can define this Tn for divide and conquer approach? So now this recurrence relation Tn can be represented or can be defined in case of divide and conquer based conquer approaches in that way. Just I have written the first step. If the given problem is a small in size or size is small, then we need to write which one. If it is a small, then it is represented as n lesser or equals to c, means the size of the problem is very small, that is smaller than a constant which you see here. If it is very small, then the running time is represented by order of 1. If the size is very small, say the size is unit, only 1, then it is represented by order of n. If the problem size is not small, then we're coming here. Problem is divided into a subproblems. Then size of each subproblem is 1 by b of the original problem. Try to understand. The problem is now divided into a subproblems. That a is a variable. And size of each subproblem is 1 by b of the original problem. Fine. That is using divide and conquer. And now if divide and conquer is applied to the merge sort, then the values of a and b becomes how much? A and b equals to 2, because the whole problem is divided into 2 parts in case of merge. That's why the value of a equals to b equals to 2. However, it doesn't mean that it should always be true. However, for other algorithms, it may be true where a not equals to b. Fine. So that is another, that is one step. And then dn equals to dividing the problem. We must have a time complexity for dividing the problem, because we are dividing the problem, it's time. But if try to understand for dividing the problem which is required, that is 1 only. That is what? That is a constant. So but here for the time being, we represent that time complexity as dn, and that is dividing the problem. And then we have a cn for which combining the subproblems. Now all the subproblems we are trying to combine now. That becomes a cn. Cn is the time complexity for combining all those problems. So now using all those things, because we have a 3-step 1, 2, 3, these all are the time complexities in the divide and conquer method. Now if you want to represent by this recurrence relation, now it can be represented as Tn equals to order of 1 if n less or equals to c. Already talked about if the size is very small. If the size is 1 only, then it becomes order of 1. Or the size is a constant only, a small, then which one? The order of n. And if it is not, if this kind divide combining all kind of things are not required, if it is not very small, then whole time complexity is represented like that. AP, this is the recurrence relation, and now this part becomes n by 2, n by b, because we have an n problem, size of the problem is n, and it is subproblem size is 1 by b. So 1 is what? 1 is the size of the original problem. That's why it becomes n by b plus dn plus cn. dn is what? This is the time complexity for divide, and this is the time complexity for which one? Combine, and this is the time complexity for the recurrence relation. Fine. Now in case of merge sort, this dn for the divide, we need to have a constant time, and it can be represented by order of 1. And in case of conquer, what do we do? In case of merge sort, 2 subproblems are solved recursively, each of size n by 2. 2 subproblems in the divide and conquer, actually in case of merge sort, 2 subproblems are solved recursively, each of size n by 2. That's why these equations for the divide and conquer becomes what? 2t n by 2. And for combine, already I told you, it arranges the elements in say ascending order. So that's why the time complexity for combine all the elements is order of n. Fine. Now we are combining all those time complexities together here. So we are writing this Tn is now especially for the merge sort now, right? Initially we started with a divide and conquer for a general problem. When the problem becomes merge sort, already we have seen that the value of A becomes 2 and the value of B becomes 2. Just we kept here 2, 2, 2, and all other things. This one for dividing order of 1, and for combining this is order of n we kept here. So finally we can write for the merge sort, if the value of n equals to 1, there is no such size, is only 1 of the sorting array, then the total time complexity that is order of 1. Otherwise this is the total time complexity here, right? And now what? Now we can combine both this and this, because already we know maximization rule. If we have order of 1 plus order of n, then it is combined edge order of n only, right? So therefore just we combine like that. So now this recurrence relation becomes this recurrence relation. Now we have assumed one thing: if constant time c is required to solve a problem of size 1, say we are looking that, and we are assuming that if the problem size is 1, then how much time is required? C constant time is required. Clear? That's why now this Tn is changed, and here the value of n equals to n. That's why the time complexity becomes C here. Clear? And now here which one? There is no change. 2t n by 2, and here we have order of n. So how many times we are combining? C number of times, right? That's why it is multiplied by C, and that's why it becomes C into n. That's it, it becomes Cn, because we assume now the constant time C is required to solve a problem of size 1. That's why now this order of n becomes like this. So finally, if we see the time complexity, the whole time complexity is represented by this one. Fine? By this one. Now see, if a recursive tree is built, because it's a recursion algorithm, it's a recurrence relation. Now if it's a recursive tree, you can say if a recursive tree is built, because it's a recurrence relation, now recursive tree can be built. If the recursive tree is built, then the total cost of the recurrence tree would be Cn log 2n plus Cn. If a recursive tree is built, I'm coming, you can have a confusion how that is actually, we're coming to sort out. So if the whole recursive tree is built, then we can see the total cost would be Cn into log 2n plus Cn. So now if we have a total cost like this is the, you can say, algebraic equation. Say from this algebraic equation, if it is represented by a function, then the whole part can be represented by big O notation, and finally we can see the whole part is represented by order of n log 2n. That's why therefore the time complexity of merge sort becomes order of n log 2n. So now we have a questions how the total cost of this recursive tree becomes like this. That's the questions now, right? So now we're looking to establish how the total cost of the recursive tree becomes Cn log 2n plus Cn. Coming to that one actually here. Already what we have assumed that the cost time, the constant time C is required to solve a problem of size 1. So problems of size 1, the time or the cost that is required is represented by C. So now coming here in the first level Tn, right? We have a Tn here. So Tn, how many elements are there? A number of elements are there. So now to sort this, level, the cost of root becomes how much? C into n, because we have an n number of elements there, and for each element we need to have how much cost? C. That's why if you find the cost of this level, it becomes C into n, and that is represented by Cn. Similarly, if we talk about the second level, in the second level, how many we're having? We are having this one. 2 into how many lists? We have 2 lists. Each of size how much? N by 2. Means in each sublist we're having n by 2 items now. Now if you find the total cost in this level, how much it becomes? 2 into, because 2 sublists are there. So 2 into C is the, for one item, this is the time, that is the cost. And number of elements, how many? N by 2. So now if we combine all those things, then in this level also the total time complexity becomes Cn. The total cost of this level becomes n. Similarly, if you find that for the ith level, we can see the total cost for this level is also Cn. And finally, at the leap level, if we count here, So these are the elements, say 1, 2, 3, 4, 5. So if we have n number of elements at the root, now if we count the total number of elements at the leaf, then we can find that the total number of elements in the root is n also. So n number of elements are there, and now for each element we need to how much cost C. So that's why if you find the cost of the last level or the leaf level, then again it becomes how much? Cn. So the conclusion is that for each level, the cost which is required in the tree, that is Cn for each level, right? That is Cn, because here Cn kind of thing. Now for a fully expanded binary tree, if you find the total number of levels, it is already established. In a fully expanded binary tree, the number of levels is represented by log 2 n plus 1. This is already established. And if you want to establish, then you have to see the mathematical part for this one, how to establish. So how many levels we can have? We can have a log 2 n plus 1 number of levels in a fully expanded binary tree. So these number of levels we are having. So coming now, so total level how much? Log 2 n plus 1. And cost for each level how much? Already established, that is Cn. So now therefore if you find the total cost, now the total cost becomes C into n log 2 n plus 1. So now if you simplify, it becomes Cn log 2n plus Cn, and this is already established. Already we have assumed this one where? We have assumed here this one, right? From here, if we find the asymptotic notation, then it can be bound by order of n log 2n. So finally, this part is proved here. Right, and these are the other algorithms using the divide and conquer. We can solve these kind of problems, binary, merge, these kind of problems we can sort out, right? And these are the time complexities. And after that, we'll have a dynamic programming. So dynamic program, I did not include any kind of problem here because to solve a problem, it requires huge time. The explanation is required and the problem becomes a bit bigger. But just roughly, I'm telling the difference between dynamic programming and the divide and conquer. In case of dynamic programming, also the whole problem is divided. When you try to understand here, the sub problem is not called recursively. Whole problem is divided into number of pieces, and all the pieces are solved and solutions are kept in a table. So whenever the solution is required, then from the table it brings. So that again and again, the computation is not required in case of dynamic programming. And also in case of dynamic programming, the sub problems are not completely independent. There are a bit of dependency in the sub problems. And especially this dynamic programming is used for the optimization problem. And these kind of problems are solved using, say, dynamic programming. Many of the problems can be solved also using some other approaches. But in most of the cases in the books, you can see those things. And then finally, we had a greedy approach. I had a many interesting thing here, but we are losing the time. I cannot, but at least I'm showing one thing. So in greedy approach is especially used if we are satisfied with the local optimal, or if the local optimum leads to the global optimum. In such a situation, greedy approach should be used because it finds locally which one is locally best. That one is taken, and once it is taken, it cannot be taken back. It cannot be altered. Even if later it can be found that some other paths or other solutions can be better, but greedy approach doesn't take care about that. It takes only the local minimum and keeps track on that, so that a problem can be solved in a faster way, and the solution may not be optimal, but at least we'll get some kind of good solution, and we can get, say, faster solution in, say, greedy approach. Now the question, when we should a greedy approach? Actually, whenever we arrive to a problem when the structure or when the problem nature of the problem is a bit, say, NP hard problem, when the problem becomes a intractable problem. What is intractable problem actually? So principally the problem can be solved, but the solutions we may get after 100 years, or the solution we can get after 10 years or the 5 years. So that kind of solution is not useful in our problem. So that kind of problem is called intractable solution, because it can be solved in principle, but the solution is not used or useful, right? So if we have this kind of problem, then to get a faster solution, we need to use a greedy approach. For an example here, I'm not talking in detail because many things are there. So in case of this one, see here, greedy approach, if we apply an exhaustive search approach here to find the best optimal path, because this This traveling salesman problem, it is well known to everybody. That's why I'm not going to discuss because it will take unnecessary time. So if we want to solve this one using exhaustive search, means we want to find all the combinations, and finally we'll take the optimal one, then the time complexity becomes, then the order of time complexity becomes order of factorial n. So whenever it becomes factorial n, then the nature becomes the NP hard. I'm not telling all factorial and all exponential are NP hard. If I can say like that, then there is a problem. NP hard not equals to P not equals to NP. This problem won't be exist, right? But still the problem exists. Can you prove P equals to NP or P not equals to NP? We cannot prove, right? But at least the problem, most of the problem which are NP, if we see their time complexity, the order is either exponential or the factorial. So if we want to solve this one using say conventional or say exhaustive method, then the time complexity becomes order of n. So in such a case, to solve such kind of problem, we can have a different kind of approaches, right? So here we can use a branch and bound to get a better time complexity than the exhaustive search. In branch and bound, what would we do? Initially, using the depth first search, we have to find one of the solution, right? So here in this case, in the traveling salesman, we are having only 4 series, right? Initially, we have taken this path, right? If we find the value of this path, then it becomes how much? This is 21. As this is a minimization problem and we got a solution, that's why this solution now represents the upper bound. This solution represents now upper bound. Now we start to find whether we get some optimal path or not using say branch and bound. So we are looking here, this path. In this path we are coming, we are looking to know this path produces a greater value than 21. So we cannot take this one. So now we can take this one. This path, this path, this path. Whenever, just I have changed the values here, try to understand to fit better for the branch and bound algorithm. So whenever we make it 12, we're looking that whenever we come here, then the total cost becomes more than 21. But we have an upper bound, that is what? 21 only. That's why this path is rejected. Then it takes this path. Looking here, it becomes 19, right? Now this path becomes how much? 19. So now earlier upper bound was 21. Now we got a path and it becomes 19. So this path is now the upper bound. Now looking here, I have changed the values intentionally, right? So whenever it contrast looks that this value is greater than the upper value, so it stops and terminates the path. Looking from here, looks that this value is greater than the upper bound. What we got? That's 19. So then terminates the path. So using branch and bound, we can get a bit better solution than when the solution is faster than exhaustive search. But still, if we calculate the time complexity, it becomes exponential. So we don't expect the solution to be exponential, because whenever it is exponential or whenever it is factorial, if the problem size is very small, when the input size is very small, we can solve the problem. This NP hard problem can be solved when the input size is very small. But you try to understand whenever the input size increases, it's the growth rate of the solution time increases drastically and unmanageably, so that we cannot manage it, right? So up to overcome from there, we have another approach, that is greedy approach. So greedy is talking about what? It's talking about I am very much satisfied with the local based solution. I don't want to have a global based solution, right? So if I am here, then I look for I have how many possibilities? I have 3 possibilities, here, here, or here. So which one is the best? This one is the best, because my objective is to solve now minimization problem. And how can I optimize the cost? How can I find the minimal path to cover all the cities at least one? So I'm coming here, this is C2. So now I'm not thinking about C3 and C4, right? I'm thinking about C2 here only. From C2, I'm looking that, no, this path is 8, this is 3. No, I'm satisfied here, because local best, if I get the local best, then I'm satisfied. So then which one? It comes here, no choice, no choice here. So in that way, actually, it can solve. And if we follow the greedy approach, then the total cost of the path becomes say 21. Rather, the situation can be say here that I have changed the situation. Even if I have a path whose cost is how much? 7, 1, 8, 9, 10. I have a path here to complete the tour with only cost 10. But if we use a greedy approach, this path is skipped. Why? Because greedy approach is satisfied or works with the immediate beta. It doesn't take care, it doesn't put any emphasis that whether this current path will be better in future or not. So that's why if we follow greedy, because this is the current best, that's why it comes in that way. It doesn't look to other ways. Now here like that. Even if we had a very good path here, that part is missed. So the conclusion is what? If we follow the greedy approach, even if you're having as a big problem and a very complex problem, the problem can be solved in a faster way, but we cannot get an optimal solution. We can get some suboptimal solution. So whenever we follow the greedy approach, we should not expect that we're going to get the optimal solution, but we need to expect that we're going to get some faster solution and feasible solution. Okay, so now if we calculate the time complexity, total becomes n square actually. Thank you everybody. I talk a lot because at last I could not discuss this problem nicely. It was very nice problem, traveling salesman problem, and using some different approaches. Not only the problem, right? If you see the book, you can get simply right. But here the objective, if we solve the same problem using different approaches, then how time complexity changes. Thank you everybody.
Students, if you have any questions, please ask.
Sir, I have a few questions, sir.
Yeah.
Sir, where can we find the good established literature for reading and understanding the design and analysis of algorithm subject?
I did not understand your question. Please again repeat the question.
Yes, sir. Where can we find the good and established literature
The book.
for reading? And, yes, sir. Book only.
Coreman is the best book, but you try to understand if you give to the student actually. Coreman is very huge. These are not summarized way. So you can look for
Yes,
the Sahani.
Sahani book. Sir, any research publications are available on these DAA subjects, sir?
Many you can get. You try to understand many. If you search in the Google, many things are there. And if somebody wants to work on that, say here heuristic search algorithm comes here, right? This part is not included. So people are using say heuristic search. Right? People are doing research on that actually. It's a part of the algorithm, heuristic search, the search technique only to reduce the time complexity. Many are working in the heuristic search, but the foundation is here actually. This is the foundation of the heuristic search, right? In such a situation, the heuristic search algorithm are used. The scientists are trying to prove, can we prove that P not equals to P equals to NP or P not equals to NP? This question is alive till now to sort out this problem only.
Sir, related question, sir. Can we say if we understand the DAA subject, understanding AI will become easy?
Very exactly. AI is what? Yeah, you have to look for the search algorithm because AI is talking about why AI is talking about from the big data. You have to find the knowledge, and those knowledge has to be represented in the memory using some models. Different kind of knowledge representation models are there. It can be rule based, it can be frame, it can be script, it can be case based reasoning, right? So when the knowledge is represented, to solve the problem actually we need to have a search algorithm, right? Yes, for example, you can see in AI there is a foundation of breadth first and depth first. These are the blind search algorithm, right? Then heuristic search algorithm comes in mind. So if the algorithm part is very clear, neat and clean, you know all the things, then you can become master of AI actually if you read carefully. Because again, in case of branch and bound, what do we do in the game playing minimax algorithm? It's nothing, it's a branch and bound. Many people don't have idea about the branch and bound in the algorithm. That's why they face number of problems in AI.
Yes, sir. Sir, another question, sir. What are the advancements in the DAA subject, sir?
Advancement means people are what people are trying. People are trying to prove some problem are NP problem or NP hard. People are trying to prove, right? So still we are having, you know, the Cook's theorem. Cook's theorem is there, right? Somehow Cook's established that CNF problem is NP complete problem. if any of the problem can be reduced in polynomial time to this CNF problem, then we can say that becomes a NP complete problem or NP problem. Fine. So still it is alive and people are trying to create more and more NP problem. So finally it can conclude the nature of NP is this and the nature of P is this. That's why actually NP problem is alive till now. So you can create number of NP problems. This is number one. Number two, in the heuristic search algorithm, you can work on that heuristic search. Many meta heuristic algorithm are there. So you try, actually main objective, people are doing some diverse thing right now, right? So using some meta heuristic, they are trying to find a accuracy kind of thing, this kind of thing. Main objective is to reduce the time complexity and the better accuracy in the heuristic search. Because heuristic search doesn't guarantee you to find the optimal solution, because only the exhaustive search can guarantee you to find optimal solution. So if we have some intractable problem, right, to track those problems, this heuristic search algorithm and a meta heuristic search algorithm, these are proposed. So people, those who are working in algorithm, they can look for developing meta heuristic algorithm or heuristic algorithm. They can understand very easily.
Yes, sir. And another question, sir. It is for students' purpose. How the students can start learning the DAA subject and what are the requirements?
I have shown the way. Actually, try to understand the way what I have shown you. This is from my experience, what I feel about the subject. In that way, actually, I made the orientation and sequence of my slide. In that way, actually, in that way, you have to know mathematical recurrence relation part means mathematics part. You have to be a bit clear on that. Only then you can find time complexity. You can understand the algorithms properly. Because algorithm subject is if you read really carefully, then this is one of the toughest subject. If you read carefully, and for the sake of pass only, then you can pass. Some problems may be given in the examination, you can pass. But to understand, this is really best and this is really toughest. And if you really understand algorithm and you can design different kind of algorithms, then it becomes the best computer scientist. The objective of the computer scientist is to design different kind of algorithms to sort out different kind of problems actually.
Yes, sir. Thank you, sir. And we want to know, YouTube channel is there, sir, for your YouTube channel is there for DAA subject, sir?
No, I don't have. Especially you try to understand. I taught it 2 years back, right? Especially I am hired. I teach actually machine learning, AI, data science, those kinds of subjects. But this is my subject of interest because I like it. I taught earlier, but how many subjects can I teach in one semester? So that's why somebody else is taking. But still, I have interest on that. The mathematical parts are huge here. And I have interest, especially whenever I read, somehow I get this algorithm kind of thing.
Any channel, any YouTube channel which will be useful for the students, or any popular and
I don't know. I don't have idea for this one, right? I don't have this one, but in YouTube you will get many machine learning materials. Whenever I conduct different kind of programs, they record it.
We
they
can find machine learning videos in your YouTube channel.
Yeah, I think videos would be available because I did one full workshop 7 days. I was only the resource person. So again, I'm telling one thing: whenever you conduct one workshop, I didn't find any kind of benefits. Whenever you invite 10, 12 speakers to conduct one workshop, then there is from the student perspective, I don't find any benefit on that. Because everybody is coming with their topic and they show them, that's over. There is no sequence, nothing. So whenever you want to have a real benefit for the student, you call somebody, and if you feel the person is good, then you tell him 1 week, 10 days or kind of thing, so that everything would be given sequentially. That's the best thing, I think.
We can make it a short-term training program like that.
Then you call somebody, right, whom you feel good, right, in that way actually. Thank you. I have a lot of schedule with me.
Can you please share the PPT which you used to demonstrate the DAA concept, sir?
Okay, I'm looking. Just okay, I'm looking. I could get your point actually. So I'm looking on that. And thank you everybody. Right? Thank you. I have really,
Your
like
lecture
I have different schedule.
Saroj
is
sir,
Yeah,
yes, sir.
who is?
Saroj sir, I have one request, sir. Can you please throw the light on NP hard and NP complete? Because I'm in 50 unit and 50 unit is NP hard and NP complete. Which problem is NP hard and which problem is NP complete problem? Like briefly, can you just tell, sir?
Again, this is so actually, see, if a problem can be solved in polynomial time, again you try to understand, there is I'm telling one thing, you can see the very good books and research paper is still there is no clear cut distinction between P and NP problem. Are you getting the point on now? So that's why the problem is open, NP not equals to NP and P equals to NP. But on an average, in most of the cases, if we have a problem, if the problem is solved in a polynomial time in a deterministic machine, in polynomial time in deterministic machine, you need to know, say, this finite automata. Deterministic machine means what? It find only the one way. Means if I am here, if you tell me in the next instance to go to somewhere else, then definitely I'll tell you I'll go there only, right? So that is actually deterministic machine. There is only one path from the initial state to final state. So if a algorithm is solved in polynomial time in a deterministic machine, then we can say that is P problem. For an example, sorting problems, knapsack problem, and different kinds of problem, these are the P problem actually. And whenever we come to the NP hard problem, it says
Hello, sir.
it must
Hello,
says
sir.
that. Yeah, yeah.
You're audible, sir. No.
So non-deterministic machine, non-deterministic Turing machine says that at a time I can search as many as I want, that number of path I can search. Means in parallel I can create as many as I want, so in parallel I can do the search. For an example, in case of traveling salesman problem, we have seen that if we solve the problem using a greedy approach, we had only one path, right, in that way. But now if we want to solve in an exhaustive search, right, exhaustive search, how many paths are created? Factorial n. So if I have a factorial n kind of possible paths at a time, then only I can solve this kind of problem in polynomial time. But unfortunately, non-deterministic Turing machine doesn't exist. That's why it says that in case of non-deterministic, in case of NP hard problem, so NP problem, we can guess any solution. We can guess any solution, guess, and then we can verify its validity in polynomial time. If we can do, then we can say this kind of problem is NP problem. On an average, people generally says whenever the time complexity is exponential or the time complexity is factorial, these are the intractable problem. And whenever it becomes intractable problem, they are generally become NP problem. But still you cannot conclude because the scientists, the research community doesn't allow and doesn't say have a consensus on that. But in most of the cases, if we have a problem, if this problem is having the time complexity that is say factorial n or say exponential, then we can say, but not straightaway. If it is, then the NP not equals to NP is solved. But in most of the cases, those kind of problem are called NP problem. For an example, traveling salesman problem, to get the optimal solution, right? It's very difficult. We cannot get click problem, CNF satisfiability problem, 3-step problem. These are the NP problem. And from NP and then NP complete, NP hard, different kind of things are there actually. In that way actually. But there is no clear distinction still. That's why still there is a research to find different kind of NP problem, So if all kind of NP problems are accumulated to a basket, and P problems are accumulated to a basket. If we can conclude something there, then finally the problem would be solved. Thank you. This is my my vision on the P and NP problem.
Thank you.
Okay, sir. Thank you, sir. I can say that, sir, like very toughest topic called asymptotic notations and the compare the time complexities, performance efficiency, and all very like easily and smoothly and clearly you have explained us. Now, moving on, we'll move to vote of thanks. Sherry, sir, will move to vote of thanks.
Thank you, madam. Thank you. Okay.
Okay, sir. So it's my pleasure and privilege to present vote of thanks. Thank you, sir, for enlightening us with your tremendous knowledge and wisdom. Definitely, it helps our students in their academics and their career. I can say that our students are fortunate to hear from you, sir. I would like to thank our principal, sir, Dr. J.P. Singh, sir, and our department academic in charge, Mrs. Shilpa, ma'am, for always supporting us to conduct such events. Special thanks to Dr. Srihari, sir, for providing us such a wonderful guest speaker. Moving on, I would also like to thank our Honorable Chairman, sir, for motivating us and providing inspiration for organizing this subject-related symposium. Last but not the least, thanks to all the students who have joined today for making this online symposium successful. Thank you all.
Thank you, madam. Thank you.
Thank you very much, sir. SarojKumarBiswas, sir. Thank you very much, sir.
Thank you, sir. Just I'm leaving, sir, because I have, sir, different schedule, sir. I'm very much busy, sir. So thank you.
Thank you very much, sir.
Thank you so much, sir.